understand about the field effect transistor, let us compare the bipolar junction transistor. Bipolar means two poles. Two poles in which way? The electrons and holes. These are the two poles or two charge carriers present in BJT. So BJT is a three-terminal device. We had base, emitter, collector. Okay. Yeah. Now the IC, which is the collector current, which is a function of the input current, that is the base current. Now we used to write IC is equal to beta IB, right? Yeah. Then yeah. Now coming to the current, the device type of the device, it is a current controlled device. The current which moves through each resistance will produce a voltage drop across this resistance. The current flowing through for example, some 1 milliampere current is flowing through this 1 kilo ohm resistance. This resistance will produce, or this current flowing through this resistance will produce 1 volt, right? 1 kilo ohm into 1 milliampere, which produces 1 volt. So the voltage is produced by the current. So it's a current controlled device. So two poles, polarity is two poles, electrons and holes, and there are two types of BJT, which is NPN transistor and PNP transistor. Okay. It is used in amplification and switching. That is the general application of or usage of BJT or transistor. Any transistor we use either for amplification or switching mainly. Okay. Now coming to the field effect transistor, it is also a three-terminal device, and the three terminals are gate, drain and source. We write it by G, D and S. Okay. Now the ID, which is the output current, that is current through drain, is a function of VGS, which is a function of voltage across G and S. Okay, gate and source. So due to this reason, FET becomes a voltage controlled device. Okay. And FET here has only one pole. It is a unipolar or one polarity. Either it has to be electron which is moving, or it has to be holes. It cannot be both electrons and holes. It is either electron or holes. So if it is electron, we call it N channel. If it is holes, we call it P channel. If it is an electron which is the carrier, we say it is N channel, or holes P channel. Use is simply amplification and switching. Some classification and properties of BJT and FET, along with another kind of FET. So JFET or JFET is a junction field effect transistor. So as we discussed, it can be two types, N channel and P channel. Now another kind of FET is MOSFET. It is metal oxide semiconductor FET. Now it can be D MOSFET or E MOSFET. These are different kinds of MOSFETs. Okay. Now comparing with the BJT, we have input impedance of FET is very high. That means input resistance for FET is very high. That means the resistance, the current that is moving, IB, is being offered a very input current is being offered a very high resistance. Okay, and it is compared to BJT, it is very high. For example, BJT would be in the terms of mega ohms, and it will be even higher. It will be 1 to 10 mega ohms for BJT, and for FET it would be from 100 to 1000. Now BJT needs small current always. That means the IB should be, there should be IB for operation of the what do you say, the BJT, while for FET, once gate terminal is charged, no more current is required. Okay, because this is charged means potential is applied. So once gate potential is applied, you get some the current or the transistor is in the on state. Now BJT has negative temperature coefficient and causes overheating. That means overheating of the transistor. But FET is a positive temperature coefficient and does not overheat. Now what is this positive and negative temperature coefficient? If the resistance is proportional to T, resistance is actually proportional to, so you can write resistivity, R equal to R naught e to the power minus alpha T. Now this alpha is positive or negative. If it is positive, resistance increases. If it is negative, the resistivity decreases with respect to temperature. T is the temperature. So if temperature increases, rho increases. This is called positive temperature coefficient. If T increases, rho decreases. This is called negative temperature coefficient. So BJT has negative. BJT follows this equation, while FET follows this particular equation. Okay. Usually, example, FET behaves like metals, while BJT is semiconductor. Both are semiconducting materials, but behaves like, that is what it means. Now BJT is used for current amplification. Mainly BJT is for current amplification and FET for voltage amplification. This is the symbol for how you can draw N channel and P channel FET. So N channel FET, here you have the direction of current towards the component. This is the FET. So if the direction of current ID is inside, it is N channel FET. If it is outside, it is P channel. Okay, the current ID if it is moving outward. So this is how symbolic representation is. Now gate terminal, the voltage from this point to this point, it is VGS, and from this point to this point, it is VDS. Okay, now this is gate, this is source, this is the drain. Drain current is the output current, generally refers to as output current of the transistor. Here also same, to the NP channel, drain current is flowing out. This is VGS. VGS is always negative. Okay, VGS has to be always negative. Now from the potential from the drain to source, it is VDS. All right. Yeah. So this is an N channel FET. So here you have N. N means lot of electrons here in this. Okay, this is P type, and here also you have P type. Now what is this gap? This gap is nothing but when two junctions are sandwiched, P and N, there is a what is this called? Barrier potential, or there is a depletion region. That depletion region is this. Okay. Now when I am sending the current, that means these electrons are moving to the other side. What happens? This region has a resistive nature. All the voltage that will be developed across these 2 points. So if I apply VDS, all the voltage will be developed across this from this point to this point, right? So if I am sending a current I, for example, this is having R, resistance R. So IR should be equal to VDS because there is no other voltage drop. Now if I am sending more current, the voltage will be higher. Now at this point, it is low voltage. At up to this point, it will have high voltage, right? So VG is the voltage applied to the gate. Now you see VG is P, okay? And what is N region? N region is here, that is drain. So this here you can write gate, and this is drain. So voltage applied between this gate and drain, you can represent it by P and N junction. Am I correct? Voltage that is being applied across P and N, or gate and drain, is nothing but P and N, voltage applied across P and N. Now here you have low potential and here you have high potential. Now you see at these ends, since it is having more potential, it will push the electrons to the N region and holes to this depletion region. So what happens is at this point you have a larger depletion region, while at the lower region you have smaller depletion region at the lower part and large depletion region in the upper part, because upper part potential is higher. Am I right? So this current ID, as ID moves through channel, potential drop occurs. Now suppose this ID equal to 0. If ID equal to 0, there is no current flowing through this channel, then there will be no drop in potential. no drop in potential. Why there is no drop in potential? Because this is having a resistive nature. So ID into R will be equal to 0. So there is no potential drop. So this will occur only if ID exists. Okay. I hope that point is clear. If this width is increased, depletion region width is increased, what happens? The electrons flow will decrease. This is just like a gate. This is usually gate, just like a gate. When gate is half closed, like this, this is the entrance, this is the gate. If the gate is closed, there will be no ID. You cannot move through it. So partially open, you can move through this gate. That is what the duty of the gate is. This gate voltage, if you increase, it will be closed. Also when ID is increasing, you cannot increase ID to a very large extent. Why? Because there will be a voltage drop happening across these ends due to increase in the source current or this ID. Okay. Now this is controlled by VGS. VGS is gate to source voltage. We will discuss the same thing. VDS is greater than 0. This potential is greater than 0. This potential is greater than 0 means there will be some flow in the circuit. This is the circuit. This one. Okay. Now VGS is 0. VGS is 0 means gate to this source is 0. Which means just like our first case, when P and N region are sandwiched, there is a depletion region. This depletion region is due to that. Okay. So after that there is no increase in depletion region. Yeah, there is no increase in depletion region because this gate VGS is 0. When we apply more voltage VGS, the depletion region may increase. But right now VGS is 0 because or there is no increase in depletion region. There will be small depletion region occurring, but that won't increase because VGS is 0. That means the gate will not be closed. Okay, gate is open. So the current flows. Once this current flows, that is from this end to the other end. So this is having a resistive nature, as we said. The current flows through this small part. Resistance will potential drop will start increasing when it moves through this resistive channel, N channel. Here you have low potential and at this point you have high potential. High potential means whatever this voltage here applied. For example, this voltage is 10 volt being applied. At this first point you will have 0, 1, 2, 3 up to 10 volt. At each point there will be a drop. So at this point you have a very high potential. So with respect to this 0 volt, our diode will be forward bias. So depletion region will start increasing at like this. Because this is N connected to P, that is negative. So this is increase in reverse bias, not forward bias, reverse bias. So depletion region will start increasing. Now how long it will start increasing? ID, there will be a maximum ID maximum will be there. Beyond that we cannot increase. If you increase beyond that, this two terminals or these two depletion region will come very close to each other, but it will not become zero. ID will not become zero. Why? Because if ID equal to 0, there will be no drop. So this voltage developed is called pinch off voltage. Voltage developed across this end such that ID equal to or ID is nearly equal to 0 is called pinch off voltage, but it will not become 0. ID equal to IDSS. IDSS means maximum saturation current into 1 minus VGS divided by VP whole square. Please remember IDSS equal to ID equal to IDSS into 1 minus VGS by VP whole square. Now please note down this formula, very important. Few questions we can discuss. Output current by input voltage. So delta ID output current by input voltage is VGS, delta VGS, that is nothing but dou ID divided by dou VGS. Now what is ID? ID equal to IDSS into 1 minus VGS by VP whole square. Please find out dou ID by dou VGS. Dou ID by dou VGS. So IDSS into 1 minus VGS by VP whole square, right? So dou ID, this is ID, dou ID by dou VGS equal to IDSS into 2 into 1 minus VGS by VP into differentiation of minus VGS by VP, that is nothing but minus 1 by VP. So that is nothing but 2 IDSS minus 2 IDSS by VP into 1 minus VGS by VP. Okay. So this is transconductance G. What is G maximum? Maximum transconductance is when VGS equal to VP. When VGS equal to VP, you will get maximum transconductance. Sorry, maximum transconductance when VGS equal to 0, and the transconductance will be 0 when VGS equal to VP. VGS equal to VP means transconductance is 0. That means no conduction. We have seen this pinch of voltage equal to VGS. So VGS equal to 0 means maximum transconductance, that is G equal to minus 2 IDSS by VP. See, so delta ID by delta VGS equal to ID this much. So 0.6 minus that is 0.4. Delta VGS 0.4 to 0.2. So that is 0.2. That is means 2 MHO transconductance. Yeah. So simple formula, right, for ID. ID equal to IDSS into 1 minus VGS by VP whole square. So IDSS is 10 into 1 minus, what is VGS? Minus 2 volt divided by VP is minus 8 volt whole square. So 1 by 4, 1 minus 1 by 4, that is 3 by 4. So 3 by 4 square is 9 by 16. So 10 into 9 divided by 16 equal to ID. Yeah. So 90 divided by 16, that is almost equal to 6. Okay. 6 milliampere. Almost, not equal. 6 milliampere. Now what is G? G equal to minus 2 IDSS divided by VP into 1 minus VGS by VP. Alright. So minus 2 IDSS is 10 divided by VP is 8. VP minus 8 you can write. Minus 8 to 1 minus VGS by VP is again 1 by 4. That is 3 by 4. So 2 into 10. So 20 divided by 8 into 3 by 4. 60 by 32. That is, you can write 5, 1. So 15 by 8. Now what is the maximum transconductance? Maximum transconductance is when this value VGS is equal to 0. That means 20 by 8. So fixed biasing. Now things that we already know about fixed biasing. Now see, here you have ID, here you have IG, the gate current, and this is IS. Now IG is also into, ID is also into. Now what is IS? The total current IS is equal to IG plus ID, right? Now but we know that it does not require, the FET does not require any input current. Input current is almost 0, equal to 0. So IG equal Ig is equal to 0, we can write Is equal to Id. Now, let us see what happens when Ig is 0. When Ig is 0, that means from this VG, this is the Ig. When Ig is 0, there is no potential drop across this Rg, which means Vrg equal to 0. If there is no potential drop, it is just like a short circuit from this Vg to the gate. Right, from the Vg to the gate, it is short circuit because there is no potential drop occurring across that end. And since it is so, we can have a equivalent circuit in this way. Here just short this Rg and we have written this value. So it's a short circuit here. You have Ig equal to 0, but let us write that. Now, so this is an equivalent circuit. Now, whatever is this VGS, that voltage is given across, or this VGS is the voltage developed across this gate and the source. Whatever it is, that will be equal to the voltage that is being supplied at here, that is VGG. You can write VGG. So if you apply Kirchhoff voltage law to this circuit, if you apply Kirchhoff voltage law, you can get VGG equal to or you can write minus because it is minus VGG equal to VGS. All right. Now again we have some more things to discuss in the output. So this is the output. VDD, this voltage VDD equal to IDRD. Let this be the current through drain, IDRD plus the voltage drop between D and S, that is equal to VDS. So what you want? VDS equal to VDD minus IDRD. But we already know what is ID. ID equal to IDSS into 1 minus VGS by VP whole squared. It's very easy. So what we know, VGS equal to minus VGG. So VGS equal to minus VGG means what is VGG? 2 volt. So that is VGS is equal to minus 2 volt. Another question is ID. You can find out ID. ID formula. IDSS. Please write the formula. Please write the formula. IDSS into 1 minus VGS by VP whole squared. So IDSS is 10 milliampere. 1 minus VGS is minus 2 divided by minus 8. Minus get cancelled. 1 by 4, 3 by 4 whole squared. So 10 into 9 by 16. So that value 90 by 16. So let us write this. Yeah, 5.6 milliampere. 5.6 milliampere is the ID. Okay. Now here you know that VG or Vs equal to 0 because it is being grounded. VGS equal to VG minus Vs, which is equal to minus 2 volt. This Vs is 0, so Vg will be equal to minus 2. So Vg equal to minus 2. Okay, now to the output. So VDS is equal to VDD minus the drop across this ID into RD. So what is VDD? VDD is 16 volt minus ID. ID we have already got 5.6 milliampere into RD. RD value is 2K. So that will be around 11.2. So 16 minus 11.2, that's equal to 4.8 volt. Okay. Now anything else is missing? VGS is done. ID, VD, VS and VG. Now what is this VD? This point, at this point is terminal. Not terminal, at this point. Voltage at a point. VD. So what is VD? Let us write what is VDS. VDS is equal to VD minus VS. What was that value? VDS, that is equal to 4.8. But you already know VS is equal to 0. So VD equal to 4.8 volt. So let us begin. So formula given, we are asked to find out this ID, that is the current through drain, G trans conductance and G max. So immediately we can write what is VGS. VGS is equal to minus VGG. So what is VGG? 2 volt. So minus 2 volt. Now once we got this value, we have ID, which is equal to IDSS into 1 minus VGS by VP whole squared. So IDSS value 10 into 1 minus VGS, that is minus 2 volt, divided by VP is 10 minus 10. That's equal to 10 into 1 minus 1 by 5 whole squared. So 4 by 5, that is 16 by 25. So 10 into 16 by 25. So 2 5 6.4 milliampere. Right, this is IDSS. Now what is G? G equal to minus 2 IDSS divided by Vp into 1 minus VGS by Vp. Yeah, so please remember this is IDSS by Vp whole squared here, and here while finding trans conductance you have minus 2 IDSS by Vp into 1 minus VGS by Vp. There is no squared, okay? Please don't get confused. This is another mistake that you are tend to make. So minus 2 into 10 milliampere divided by Vp is again 10. You can write minus 10 into 1 minus VGS, that is minus 2 divided by minus 10. So 10 get cancelled. So minus 2 into, sorry, plus 2 into 1 minus 1 by 5, that is 4 by 5. 8 divided by 5, that is around 1.6 millimho, because this is IDSS is in milliampere. So millimho. G maximum is equal to minus 2 IDSS divided by Vp, only this much. So minus 2 into 10 divided by minus 10, that's equal to 2 milliohm. So maximum transconductance is 2. Transconductance value is 1.6. Now as usual our Ig value equal to 0, then Rg is short circuit, short. Now just applying the KVL to the input. This is the input. V minus VGG, minus VGG, this is VGG, okay. Minus VGG equal to, why it is minus? Because it is giving out a negative terminal, that means negative potential. So minus VGG equal to the drop across, this is 0, right? Drop across, this is 0. So VGS plus IS into RS. IS into RS. So what you want? You want VGS. VGS is important for us. Why? Because it is the one which regulates the current. Alright. So VGS is equal to minus VGG minus IS times RS. Now this IS we can write it as IS equal to ID. Why ID? Because Ig equal to 0. So VGS, important formula for self biasing, minus VGG minus ID into RS. Now this is for input. So let us find out for output also, KVL. Alright. VDD equal to ID into RD plus VDS plus IS into RS. This IS we can write it as ID. Don't change it here, you change it later. ISRS. So that is VDD equal to IDRD and IDRS. So ID into RD plus RS plus VDS. So what you want here? VDS. VDS is equal to VDD minus ID into RD plus RS. Another formula to remember for self-biasing. So what we have done for BJT in voltage divider bias, we have considered this as VDD and this is also VDD and this is removed. This terminal is removed or this connection is removed. Now this resembles a Thevenin's equivalent circuit if you are finding out R2. Alright, am I correct? This is R2. Across R2 what we are finding. So voltage across R2 is nothing but VTH. What is VTH? So VDD into R2 divided by R1 plus R. Now here you have RG. What is RG? RG is nothing but R1 R2 divided by R1 plus R2. Thevenin's equivalent circuit. Now just replace this VGG by VR2 or VTH and this RG divided by, you can write R1 R2 or you can write RTH also, RTH. Then this is very similar to our self biasing. Please find out. So let's start. VGG equal to VTH. See, write it as VTH, you will not forget. So VDD into R2 divided by R1 plus R2. Now you see 20 into R2. What is R2? 20. K also you can write, but no need. It will get cancelled. R1 plus R2 is 10 plus, sorry, R1 plus R2 means 80 and 20, that is 100. So 4K, that is RG. Sorry, this is 4 volt. That is VGG. That is, and what is VGS? VGS is equal to minus VGG, that is equal to minus 4 volt. Okay. Now RTH, actually no need, but we can write RG equal to 80 into 20 divided by 100. 16K. Alright. Now then we can write the equivalent circuit, or Hmm. So what is the volt here? 4 volt. 4 volt is equal to RTH or RTH into Ig. This value is equal to 0 plus VGS plus ID into RS. Now here VGS is there, no, that you can write. So VGS equal to 4 volt minus this particular value is 0 minus ID into RS. Now this is fine. Now once you got VGS, what is VGS? ID you want. So VDD value will not change, 20 volt. This RD is given to be 3K and RS is given to be 2K and VGG, that is 4 volt, and RG is 16K. Okay, now this is what is VDS and this is VGS. So VGS equal to 4 minus ID into 2K. ID into 2k VGS is equal to any parameters is missing from here. Okay, let us apply to output also first. Output 20 volt is equal to ID into 3k plus VDS plus ID into RS. Why ID into RS? Because ID is same as R. Okay. So that's equal to ID into I is ID into 3 plus 2. RS is 2k. 2k. So 5k plus VDS. ID into 5k. So VDS is equal to 20 minus ID into 5k. Just let me check if there is any other term is given. Without giving this value VGS, we cannot find.